Imagine standing on the equator, looking up, not at a sky full of stars, but at a single, impossibly thin line stretching from the Earth's surface, vanishing into the blackness beyond the atmosphere. No roaring engines, no plumes of fire, just silence and a ribbon of carbon climbing all the way to space. What if getting to orbit wasn't a violent explosion of fuel and heat, but a gentle, quiet ride, like an elevator? This isn't fantasy, it's not magic. It's a real idea, born not in a Hollywood studio, but in the notebooks of scientists and dreamers who asked a simple question: why do we have to fight gravity with brute force when we could simply climb out of its grip? For over a century, humanity has blasted itself into space using rockets machines that must carry everything they need: fuel, oxidizer, structure, just to fight their way through the first few dozen miles of atmosphere. Over 90% of a rocket's mass at launch is fuel, burned in minutes, gone forever. And for what? To reach a place just 200 miles up that we could, in theory, reach with nothing more than a very, very long cable. The space elevator is the ultimate act of cosmic rebellion, not against nature, but against inefficiency, against waste, against the idea that space must remain distant, expensive, and dangerous. It promises to turn the journey to orbit into something as routine as taking the subway, as mundane as commuting to work. And if it works, it could change everything. But here's the catch: no one has built one, not because we lack the vision, but because we lack the material, the strength, the precision, the will, and because space does not forgive mistakes. So today, we ask the question that has haunted engineers, physicists, and science fiction writers alike: could a space elevator actually work? Not in a distant future, not with alien technology, but with the science we know, the materials we have, and the laws of physics that govern our universe exactly as they are. This is not a story about what might be possible in 10,000 years. This is a story about what might be possible in our lifetimes. The idea feels modern, futuristic, but its roots stretch back farther than you might think. In the late 1800s, decades before the first airplane even left the ground, Russian visionary Konstantin Tsiolkovsky looked up at the sky and imagined a celestial castle held aloft by a tower anchored to Earth and stretching tens of thousands of miles into space. He didn't call it a space elevator, but he saw the principle: use the Earth's rotation itself as a source of upward force. A century later, in the 1970s, science fiction legend Arthur C. Clarke brought the idea to the masses in his novel The Fountains of Paradise. There, he described a orbital tower, a structure so tall it reached geostationary orbit, with cars gliding silently along its length. Clarke famously said, "The space elevator will be built about 50 years after everyone stops laughing. We're still waiting, but we're not laughing anymore. Because now we're not just dreaming, we're calculating, testing, simulating." And the answer is more complicated and more thrilling than anyone imagined. This journey won't be about hype or blind optimism. We'll confront the brutal physics, the terrifying risks, the material science that borders on the impossible. But we'll also explore why this idea refuses to die. Why, despite every obstacle, some of the smartest minds on Earth keep returning to it, like a siren song from orbit. Because if it works, if we can build a bridge from our planet to the stars, then humanity won't just visit space, we'll live in it. So let's begin, not with equations, but with wonder. What would it feel like to ride the sky? At first glance, the space elevator seems to defy common sense. Hang a rope from the sky, anchor it to the ground, let payloads ride it like a tram to orbit. It sounds like trying to balance a pencil on its tip, except the pencil is 36,000 kilometers long and spinning at 1,670 kilometers per hour. But here's the secret. The space elevator doesn't defy physics. It uses physics precisely, elegantly, and ruthlessly. The key isn't strength alone, it's balance. Imagine tying a ball to a string and swinging it around your head. The ball wants to fly off in a straight line. That's inertia. But the string pulls it inward, forcing it into a circle. That inward pull is tension. Now, if you let go, the ball flies away. But if you keep spinning, the tension remains. Now scale that up, way up. The Earth spins once every 24 hours. At the equator, the surface moves at about 1,670 kilometers per hour. Not fast enough to fling us into space, but fast enough that if you go high enough, something strange happens. At an altitude of exactly 35,786 kilometers, what scientists call geostationary orbit, an object circles the Earth in exactly 24 hours. It stays fixed over the same point on the equator. From the ground, it appears motionless in the sky. This is the sweet spot, the pivot, the fulcrum of the entire system. Now, imagine lowering a cable from that point down to Earth. Gravity pulls it down. But because the top is moving with the Earth's rotation, centrifugal force tries to fling it outward. Below geostationary orbit, gravity wins. Above it, centrifugal force dominates. So if you attach a massive counterweight beyond geostationary orbit, say at 50,000 kilometers, the whole system balances. The counterweight pulls the cable taut while Earth's gravity holds the base in place. The result? A stable, taut structure stretching from the surface through the atmosphere, past the Van Allen belts, and deep into space. It's not hanging down from space, it's being held up by spin. But this balance is delicate, exquisitely so. The cable isn't uniform. It can't be. Near the ground, it must support the entire weight of the cable beneath the geostationary point. Higher up, near the counterweight, it must withstand the outward tug of centrifugal force. So the cable must be thickest at geostationary orbit, where tension peaks and taper toward both ends. Engineers call this the taper ratio. And it's brutal. For steel, the taper ratio would be something like 10 to the power of 50. That means if the cable were 1 millimeter thick at the top, it would need to be wider than the observable universe at geostationary orbit. Obviously impossible. Even Kevlar, stronger than steel by weight, fails catastrophically. Its taper ratio is still over 100 billion. But there's hope, because physics doesn't forbid strong materials. It just demands they meet a minimum threshold, a specific strength measured in Uri. 1 Uri equals 1 meter squared per second squared. Basically, how much load a material can hold per unit density before breaking under its own weight. To build a space elevator with a reasonable taper ratio, say under 20, the cable material needs a specific strength of at least 40 million Uri. Steel? Around 0.5 million Uri. Kevlar? About 2.5 million. Carbon nanotubes? Theoretically, up to 100 million Uri. Ah, there's the dream. But theory and reality are not the same. We'll get to materials soon. But first, understand this. The space elevator isn't a building. It's not a tower. It's a dynamic, rotating, tension-based structure, more like a spinning lasso anchored to a planet. And every part of it must obey Newton's laws without compromise. If the counterweight is too light, the cable sags. If the base isn't perfectly on the equator, the whole thing wobbles like a plucked guitar string. If the climber moves too fast, it creates waves that could snap the cable like an overtuned violin string. Even the moon's gravity tugs on it. So do solar winds. So do passing satellites. This isn't just engineering, it's orbital ballet with zero room for error. And yet, the physics checks out. No new laws need to be invented, no magic required, just precision, patience, and a material that can endure unimaginable stress without yielding. So the question isn't whether physics allows it. The question is, can we build it? And that brings us to the heart of the problem, not the idea, but the thread. Every great structure begins with a single thread. The pyramids rose from stone, skyscrapers soar on steel. But the space elevator? It demands something no human has ever held in their hands, a material so strong, so light, so perfect that it borders on myth. For decades, this was the wall, the dead end, the reason the space elevator lived only in novels and dreams. Because here's the truth, if you tried to build this with any material we used before the year 2000, it would snap under its own weight before reaching even 1% of the required height. Steel, as we've said, it fails by a factor of 80. Aluminum. Worse, even the best aerospace alloys dissolve into irrelevance when you stretch them thousands of kilometers into the void. We needed a revolution, not in design, but in substance. And for a brief, shining moment, it seemed we'd found it. In the early 1990s, scientists discovered carbon nanotubes. Cylinders of carbon atoms rolled into seamless tubes, each thinner than a human hair, but stronger than anything known. In theory, a single perfect nanotube could lift 50,000 times its own weight. Its specific strength, up to 100 million Uri. Exactly what the space elevator needed. The dream flared back to life. Conferences were held, competitions launched. NASA even sponsored the Centennial Challenges, offering cash prizes for the strongest tether materials and the fastest climbers. Hope surged. But then reality set in, because making a single nanotube in a lab is one thing. Weaving billions of them into a ribbon 40,000 kilometers long without a single defect is another. Here's the cruel twist of material science. Strength isn't just about what something can be, it's about what it is at scale. A flawless diamond is the hardest natural substance on Earth, but introduce a single crack, it shatters. Same with carbon nanotubes. In the lab, individual nanotubes exhibit near-perfect atomic alignment. But when you try to bundle them into fibers or sheets, they tangle, they misalign, they develop weak spots, impurities sneak in, and strength plummets. The best carbon nanotube fibers made to date achieve only about 10 million Uri, just 1/4 of what's needed. And that's in short lab samples, centimeters long. Now imagine scaling that up. 40,000 kilometers is, well, picture this. If you laid the cable end to end, it could wrap around the Earth's equator and still have enough left over to reach the moon. Keeping that material flawless over that distance, with current technology, impossible. But scientists didn't stop there. Enter graphene, single-layer sheets of carbon atoms arranged in a honeycomb lattice, even stronger than nanotubes in theory, but just as hard to manufacture at scale. Or boron nitride nanotubes, more heat-resistant, but even harder to produce. Or diamond nanothreads, predicted to be stronger still, but so far only created in microscopic quantities under extreme pressure. All of them live in the realm of promising, in principle. None of them live in the realm of ready to build a skyladder. And then there's another problem, the environment. Space isn't empty. It's full of radiation, atomic oxygen, micrometeoroids, and temperature swings from -150 degrees Celsius in shadow to +150 in sunlight. Any real space elevator cable would be constantly bombarded, eroded, weakened. Even if we had a perfect material today, could it survive decades in orbit? We don't know, because we've never tested it. But wait, what if we didn't need perfection? Some researchers suggest using a safety factor. Build the cable thicker than strictly necessary. Accept that small failures will occur and design redundancy into the system, maybe even self-healing polymers that seal micro-tears. Others propose starting small, not a full elevator to geostationary orbit, but a lunar space elevator where gravity is weaker and the engineering far more forgiving, or a Martian version with only 38% of Earth's gravity. But Earth is the ultimate test, and so far the material remains the gatekeeper. Yet something remarkable is happening. In labs from Tokyo to Texas, researchers are inching forward. In 2023, a team in China reported a carbon nanotube fiber with a tensile strength of over 8 gigapascals, the highest ever recorded. Still not enough, but closer. And new techniques like shear spinning and gel spinning are producing more aligned, stronger fibers than ever before. It's slow, painfully slow, but it's progress. So the question isn't if such a material can exist. Physics says yes. The question is, when can we make it? And more importantly, will we make it in time to seize the opportunity before us? Because even if we solve the material problem, the cable is only part of the story. It needs an anchor, a counterweight, a path through chaos. And those are battles of their own. A space elevator isn't just a cable. It's a system, alive, dynamic, and exquisitely balanced between opposing forces. And like any system in tension, it needs two things, something to hold it down and something to pull it up. That's where the anchor and the counterweight come in. On one end, the earth end, the cable must be bolted to something immovable, not just a platform, but a fortress. Because this isn't a mooring for a boat, it's the foundation of a structure that reaches deeper into space than any human-made object ever has. And it can't just sit anywhere. It must sit precisely on the equator. Why? Because only on the equator does the Earth's rotational axis align perfectly with the plane of geostationary orbit. Move even a few degrees north or south, and the cable begins to wobble. It experiences lateral forces. It starts to whip. And a 40,000-kilometer whip made of ultra-strong material? That's not a structure, that's a weapon aimed at the planet, so the anchor must be mobile but constrained. Most designs place it on a floating platform in the equatorial Pacific, far from shipping lanes, air traffic, and political borders. Think of it as a supertanker-sized base, stabilized by thrusters, able to drift slightly to avoid storms or space debris. It would house power stations, control rooms, and climber launch bays. But it would also be vulnerable. Hurricanes don't cross the equator, but typhoons and cyclones come close. Lightning, constant. Salt corrosion, relentless. And then there's human risk, sabotage, terrorism, or simple bureaucratic collapse. One nation deciding to deny access could sever humanity's sky road. So the anchor isn't just engineering, it's geopolitics. Now, look up. Far above, beyond geostationary orbit, at around 50,000 kilometers or more, hangs the counterweight. This isn't optional. It's essential. Without it, the cable would simply fall. The counterweight provides the outward centrifugal force that balances Earth's inward pull. It's the anchor in the sky. What could serve as a counterweight? Option 1, a massive object launched from Earth like a captured asteroid or a spent spacecraft stacked with lead. But launching that mass defeats the purpose of the elevator in the first place. Option 2, extend the cable beyond geostationary orbit and let the extra length act as its own counterweight. The farther out you go, the stronger the centrifugal force. At around 100,000 kilometers, even a modest mass suffices. But there's a third, more elegant idea: use a captured near-Earth asteroid. Imagine this. A small metallic asteroid, maybe 500 meters across, is nudged into position over decades using ion thrusters. Once in place, it becomes the keystone of the entire system. Not just dead weight, but a future mining outpost, fuel depot, or deep space launch platform. Suddenly, the counterweight isn't a cost, it's an asset. But here's the fragile truth. The cable connects these 2 points, not like a rigid rod, but like a violin string. And like any string under tension, it vibrates. When a climber ascends, carrying cargo or people, it doesn't just move upward. It pulls on the cable. That pull sends waves traveling up and down the tether-like, plucking a guitar string thousands of kilometers long. If those waves resonate, if they sync with the natural frequency of the cable, they could amplify into destructive oscillations. The cable might whip, tangle, or even snap. So climbers can't just race upward, they must move slowly, carefully, in coordination. Engineers would need to choreograph their journeys like conductors managing an orchestra, dampening vibrations with active stabilizers, or by timing departures to avoid harmonic buildup. And the cable itself. It would likely be designed with slight flexibility or even segmented sections with dampers to absorb these shocks. Then there's the issue of Earth's gravity field, not perfectly smooth. It has bumps and dips caused by mountains, ocean trenches, and dense rock formations. These gravity anomalies tug unevenly on the cable as the planet rotates, introducing tiny but persistent perturbations. Over time, those perturbations could nudge the anchor off-center or twist the cable into a slow corkscrewing motion. So the base station wouldn't just sit still. It would constantly adjust using GPS, gyroscopes, and thrusters to keep the entire system centered over the equator. It would be a dance, a silent, high-stakes ballet between rock, metal, and void. And through it all runs that single, fragile ribbon, thinner than your thumb at the surface, yet bearing the weight of humanity's future. It must hold, not for minutes, not for days, but for decades. Because if it breaks, the consequences are catastrophic. And we'll get to that. But for now, understand this. The space elevator isn't held up by strength alone. It's held together by balance. By the perfect opposition of gravity pulling down and spin flinging out. One anchor in the sea, one weight in the stars. And between them, the thinnest line between miracle and disaster. It's tempting to picture the space elevator like a beanstalk from a fairy tale rooted in the soil, stretching straight up into the clouds, waiting for a brave climber to scale it. But space doesn't work that way. There are no clouds. No, up in the way we think of it, and nothing in orbit just hangs there. Everything moves, everything orbits. And the space elevator, despite looking static from the ground, is actually hurtling through space at tremendous speed, locked in a cosmic balancing act that defies intuition but obeys Newton with ruthless precision. Let's clear up a myth first. The cable does not point straight up like a pencil, because the Earth is spinning, and the top of the elevator is moving faster than the bottom. Wait. How can that be? Think of a record player. Place a dot near the center and another near the edge. Both complete one rotation in the same time, but the outer dot travels a much longer path, so it moves faster. Same with the space elevator. The base, anchored on the equator, spins with the Earth about 1,670 kilometers per hour. But the counterweight, tens of thousands of kilometers out, must complete one full circle every 24 hours too. To do that, it has to travel much farther in the same time. So its orbital speed is over 10,000 kilometers per hour. That difference in speed creates tension along the cable. And that tension is what keeps the whole thing taut. But here's where it gets stranger. If you cut the cable at geostationary orbit, The 35,786-kilometer mark, the lower half would fall straight down to Earth. The upper half, it wouldn't just float. It would fly off into space because its speed is greater than the escape velocity at that altitude. That's how finely tuned the system is. Now consider what happens when you send a climber up the cable. As it rises, it's not just gaining height, it's gaining angular momentum. It's being dragged eastward faster and faster by the spinning cable. By the time it reaches geostationary orbit, it's moving at exactly the right speed to stay in sync with Earth's rotation. But if it goes higher, it's now moving faster than orbital velocity for its new altitude. That means it wants to fly outward, adding more tension to the upper cable. Conversely, if a climber descends, it slows down relative to orbital speed. It begins to lag, pulling the lower cable slightly westward. Each climber, then, doesn't just ride the elevator. It changes the elevator's dynamics. That's why you can't just send climbers whenever you like. You need to balance ascents and descents. Maybe send empty climbers down while loaded ones go up, so the net transfer of momentum stays near zero. Otherwise, the whole system starts to drift. The anchor gets tugged off the equator. The cable begins to precess, like a slowing top, wobbling in a slow, dangerous spiral. And once that wobble starts, it's hard to stop. Then there's the moon. Yes, the moon. Its gravity tugs on the cable every single orbit, about every 27 days. Not enough to snap it, but enough to induce slow, rhythmic oscillations. Over months, those could build up. Solar radiation pressure adds another nudge, especially on the upper sections, where sunlight pushes against the cable like wind against a sail. And don't forget Earth's equatorial bulge. Our planet isn't a perfect sphere, it's slightly fatter at the equator. That uneven mass distribution creates subtle gravitational tugs that twist the cable's orbit over time. All of this means the space elevator can't be passive, it must be active. Sensors along its length would monitor strain, vibration, and position. Thrusters on the counterweight could fire tiny bursts to dampen oscillations. The anchor platform would shift slightly to counteract lateral forces. It would be a living structure, constantly adjusting, correcting, listening to the whispers of gravity and motion. And yet, despite all these forces, the math holds. Engineers have run simulations for decades. With proper control systems, the space elevator can remain stable. Not perfectly still, but stably dynamic. Like a tightrope walker using a pole to stay balanced in a breeze. But this stability comes at a cost: complexity. Every added system, thrusters, sensors, dampers, is another point of failure. Another thing that must work perfectly for decades in the harshest environment imaginable. And if one part fails, the whole system could unravel. So no, the space elevator doesn't just hang there, it dances. A silent, high-speed waltz with gravity, inertia, and time, where one misstep could send 40,000 kilometers of cable whipping across continents like a cosmic whip. To build it, we must not only understand orbital mechanics, we must master them, and even then, the sky itself may fight back. The space elevator wouldn't just be an engineering marvel, it would be a target. Not by choice, but by necessity. Stretching from the ocean's surface through the densest part of the atmosphere, past low Earth orbit, through the radiation belts, and into the silent void beyond, it would intersect every major hazard zone known to spaceflight, and each one could kill it. Let's start from the ground up. At the base, where the cable meets the ocean platform, lies the fury of Earth itself. Lightning doesn't strike just once. In equatorial regions, thunderstorms rage almost daily. The cable, thin and conductive, would act like the world's tallest lightning rod. A single strike might not break it, but repeated strikes. They'd erode the surface, create microfractures, and induce electrical surges that could fry climber electronics or destabilize control systems. Then there's wind, not just breezes, but cyclones. While true hurricanes don't form right on the equator, tropical storms can skirt close enough to generate 100-kilometer-per-hour gusts. The lower 5 kilometers of the cable would sway like a harp string in a gale. If the anchor platform can't compensate fast enough, resonant vibrations could travel upward, amplifying into destructive waves. Corrosion is quieter, but no less deadly. Salt spray, humidity, and atmospheric oxygen eat away at even the most advanced materials. Over years, that slow decay could weaken the cable's base, the very point under the highest gravitational load. Now climb higher. Between 100 and 2,000 kilometers up low, Earth orbit, the cable passes through humanity's orbital junkyard. There are over 500,000 pieces of trackable debris larger than a marble. Millions more too small to see, but moving at speeds of up to 28,000 kilometers per hour. At those velocities, a paint fleck can crack a spacesuit visor. A bolt, it could slice through steel like paper, and the space elevator cable, though incredibly strong, has almost no width to spare. A direct hit from even a 1 centimeter fragment could sever it. Worse, the cable can't dodge. It's fixed in place. Unlike satellites that can fire thrusters to avoid collisions, the elevator is a sitting duck. Some engineers propose debris shields, sacrificial layers that absorb impacts. Others suggest giving the cable slight lateral mobility, using electromagnets or thrusters to nudge it a few meters when a collision is predicted. But that requires flawless tracking of every piece of debris and flawless response time. Today, we can't reliably track objects smaller than 10 centimeters. Yet something as tiny as a screw traveling at orbital speeds carries the kinetic energy of a hand grenade. And the problem is growing. With mega constellations like Starlink launching thousands of new satellites, low Earth orbit is becoming more crowded by the year. The chance of a catastrophic strike rises with every launch. Higher still, between 2,000 and 6,000 kilometers, the cable cuts through the inner Van Allen radiation belt. Here, Earth's magnetic field traps high-energy protons and electrons. Prolonged exposure fries electronics and degrades most materials. Climbers would need heavy shielding. The cable itself would need radiation, resistant coatings, adding weight, complexity, and potential failure points. Then there's atomic oxygen, the single most erosive element in low orbit. It's not the oxygen we breathe, but a hyper-reactive form created when sunlight splits off fire molecules. It eats away at polymers, composites, even some metals. Over decades, it could sandblast the cable's surface into brittleness, but the ultimate threat might not come from nature at all. It could come from us. Imagine a rogue state launching a missile, not at a city, but at the cable. A single kinetic impactor, even a small one, could trigger a global catastrophe. Or a hacker infiltrating the climate control system, causing a collision or deliberate overload. Or a terrorist group sabotaging the anchor platform. Unlike a rocket launch, which is fleeting and hard to intercept, the space elevator would be a permanent, visible symbol of human ambition. And permanence invites attack. Even peaceful protests could turn dangerous. What if activists block the base? What if a nation claims the cable violates its airspace? The geopolitical risks are enormous. And if the cable does break, the consequences depend on where it snaps. If it breaks below geostationary orbit, the lower portion falls to Earth, wrapped around the planet like a slow-motion lasso. Depending on the breakpoint, it could wrap across continents, slicing through forests, cities, or oceans. Not with explosive force, but with terrifying, unstoppable momentum. If it breaks above geostationary orbit, the upper section, still under centrifugal tension, flies outward into deep space, possibly becoming a new piece of interplanetary debris. But the worst-case scenario? A break near geostationary orbit. Then both ends go wild. The lower part crashes down in a chaotic spiral. The upper part whips outward, potentially colliding with satellites or even the moon over centuries. It wouldn't be just a failure. It would be a planetary-scale accident. So yes, the space elevator is vulnerable, from lightning below to micrometeoroids above, from human error to human malice. It would need layers of defense, real-time debris tracking, lightning diverters, radiation, hardened materials, cybersecurity protocols, and international treaties treating it as a protected global asset, like undersea internet cables, but far more critical. Because once built, it wouldn't just belong to one nation, it would belong to civilization, and civilization would have to defend it with everything it has. Imagine a world where launching a kilogram into orbit costs not tens of thousands of dollars, but tens. Not because rockets got cheaper, though they have, but because we stopped using them for routine access altogether. That's the promise of the space elevator. It wouldn't just be a marvel of physics, it would be an economic earthquake. Right now, even with reusable rockets like SpaceX's Falcon 9, sending mass to low Earth orbit costs roughly $5,000 per kilogram. To geostationary orbit, closer to $20,000. And that's the best case. For government missions or specialized payloads, it can soar far higher. Why so expensive? Because rockets are single-use fireworks. Most of their mass is fuel burned in minutes, and even reusable parts require extensive refurbishment. But a space elevator changes the equation entirely. Once built, its operating cost would be dominated by electricity powering the climbers as they ascend. A climber moving at 200 kilometers per hour might use about 10 megawatts of power. Over a 5-day trip to geostationary orbit, that's roughly 1,200 megawatt hours, worth about $120,000 at industrial electricity rates. Spread that over a 20-ton payload? That's just $6 per kilogram. Yes, 6, not 6,000, 6. Of course, that ignores the colossal upfront cost. Estimates vary wildly, from $20 billion to over $100 billion. That's more than the International Space Station, more than the Apollo program in today's money. But consider this, the global space economy is already worth over $500 billion and projected to exceed $1 trillion within a decade. Satellite internet, Earth observation, space manufacturing, lunar missions, all are bottlenecked by launch costs. The space elevator wouldn't just serve existing markets, it would create entirely new ones. Imagine building massive solar power stations in orbit, kilometers wide, beaming clean energy down to Earth. Today, that's science fiction because launching the required mass is prohibitively expensive. With a space elevator? Suddenly feasible. Or space-based factories producing ultra-pure fiber optics, exotic alloys, or pharmaceuticals in microgravity. Products impossible to make on Earth. Or refueling depots in orbit, enabling affordable missions to the Moon, Mars, and beyond. The elevator wouldn't just lower the cost of access, it would multiply the value of what we do in space. And the revenue wouldn't come from cargo alone. Passengers could ride too. A 5-day ascent, smooth, silent, with panoramic views of Earth shrinking below, could become the ultimate luxury experience. Tickets might start at $50,000, then drop as capacity grows. Not just for tourists, but for scientists, engineers, and orbital construction crews who currently endure violent rocket launches. No G-forces, no vibration, just a gentle climb into the cosmos. But who would pay for it? No single company could shoulder $100 billion risk. Even SpaceX or Blue Origin would balk. This would require a global consortium, governments, private firms, international agencies, sharing cost, risk, and reward. Think of it like the Transcontinental Railroad, or the Suez Canal, or the Internet backbone. Infrastructure so transformative it demands collective investment, and once operational, it would pay for itself. At just 100 tons launched per day, a modest estimate, the elevator could generate over $2 billion in annual revenue at $50 per kilogram. At full capacity, potentially 10 times that. The return on investment? Decades, yes, but with near zero marginal cost after construction. It would be the ultimate toll road to the stars. Critics argue, we don't need it yet. Rockets are good enough. But history says otherwise. In the 1800s, sailing ships crossed the Atlantic just fine. But the steamship didn't just make travel faster, it made it reliable, scalable, and accessible. It birthed globalization. The space elevator is that leap. Rockets are the age of sail. The elevator? The age of rail. There's another economic twist. It could democratize space. Right now, only wealthy nations and corporations can afford orbit. But with cheap, routine access, universities in Kenya, startups in Vietnam, or artists in Brazil could send experiments, satellites, or even habitats into space. The barrier wouldn't be money, it would be imagination. But this future hinges on one brutal truth: the elevator must be built before alternatives make it obsolete. What if nuclear thermal rockets cut launch costs to $100 per kilogram? What if spaceplanes finally work? Possible, but unlikely to beat $6. More likely, the elevator and rockets coexist. Rockets for urgent, high-thrust missions like crew, escape, or planetary launches. The elevator for bulk cargo, fragile instruments, and long-term infrastructure. They'd be complementary, not competitors. So yes, the economics are staggering. Not just in savings, but in opportunity. The space elevator wouldn't just be a machine, it would be an engine of civilization-scale growth. But only if we're willing to invest not just money, but trust. Because money can be raised. Trust between nations, companies, and generations is far harder to build, and far easier to break. Still, the numbers don't lie. If we can build it, we should build it. Not for glory, but for return, for access. For the simple, revolutionary idea that space should belong to everyone, not just those who can afford a rocket. For years, the space elevator lived in the liminal space between fantasy and fringe science, dismissed by mainstream engineers, adored by futurists, and relegated to the back pages of aerospace journals. But quietly, persistently, a small global community has been turning dream into design. Not with billion-dollar budgets, but with whiteboards, simulations, and backyard experiments. The turning point came in the early 2000s, when NASA's Institute for Advanced Concepts began funding serious studies. Then, in 2005, the Spaceward Foundation launched the Elevator 1,000-ton competition, offering prizes for the strongest tether and the fastest climber. Teams from MIT, the University of Saskatchewan, and even high schools in Germany entered. They didn't build space elevators, but they built proofs of concept. Tiny climbers powered by lasers, tethers made of Xylon and spectra, precision control systems that could track a moving ribbon from meters away. It was modest, but it was real. Today, the most active research isn't in the United States, it's in Japan. The Japan Space Elevator Association, JSEA, has held annual competitions since 2008. University teams build palm-sized climbers that race up nylon tethers suspended from balloons or towers, powered by ground-based lasers or microwaves. In 2016, a team from Nihon University launched a miniature climber into the stratosphere using a weather balloon, testing deployment and communication at near-space altitudes. And in 2023, JAXA, the Japanese space agency, quietly included space elevator feasibility in its long-term roadmap, alongside lunar bases and Mars missions. Why Japan? Partly cultural. Japan has a deep tradition of precision engineering and long-term thinking. Partly practical. With limited land and resources, it sees space not as a frontier to conquer, but as a necessity to access. But Japan isn't alone. In China, state-funded research labs have published papers on carbon nanotube production specifically for orbital tether applications. In 2021, a Chinese team demonstrated a continuous spinning process that created meter-long nanotube fibers with record-breaking strength. In Europe, the International Academy of Astronautics released a comprehensive space elevator feasibility study in 2019, concluding that while materials remain the bottleneck, no fundamental physics barriers exist. Even private companies are inching closer. Liftport Group, a US-based startup, has been advocating for the elevator since 2003. Though it hasn't built hardware at scale, it runs climber simulations and public outreach campaigns. And then there's the Obayashi Corporation, one of Japan's largest construction firms. In 2012, it stunned the world by announcing a goal to build a space elevator by 2050. Not a maybe, not a someday, a corporate timeline. Their plan: use carbon nanotubes once matured to build a cable just 9 centimeters wide at its thickest point. Climbers would carry 30 passengers or 20 tons of cargo at 200 kilometers per hour. Power would come from ground-based lasers beamed to photovoltaic panels on the climbers. And the cost? Estimated at 1 trillion yen, about $9 billion at the time. Ambitious? Absolutely. But coming from a company that built the Tokyo Skytree and bullet train tunnels through mountains, it's not pure fantasy. So what's the realistic timeline? Most experts agree. Not before 2040. Why? Because material science moves slowly. We're not waiting for a eureka moment. We're waiting for incremental progress. Better alignment of nanotubes, cleaner synthesis processes, scalable manufacturing. Think of it like the transistor, invented in 1947, but it took decades to miniaturize and mass produce. Carbon nanotubes are in that same valley of disappointment, promising in theory, frustrating in practice. But progress is happening. In 2024, researchers at the University of New South Wales achieved a breakthrough in welding. Nanotubes end-to-end using electron beams, reducing weak junctions. At Rice University, scientists are growing nanotubes directly into continuous fibers using floating catalyst chemical vapor deposition, a method that could one day be industrialized. None of this guarantees success, but it keeps the door open, banned. If materials don't pan out, alternatives are being explored. One idea: build a partial elevator, not to geostationary orbit, but to just above the atmosphere, say 100 kilometers up. At that height, a rocket or spaceplane could take over for the final push to orbit. This skyhook concept reduces the cable length dramatically, easing material demands. Another: start on the moon. With 1/6 Earth's gravity and no atmosphere, a lunar space elevator is vastly simpler. A cable just 50 kilometers long could fling payloads into cislunar space using centrifugal force alone. NASA has studied this for Mars missions, using the moon as a low-cost launch point. Mars is even more promising. Its gravity is 38% of Earth's, and its rotation is just slow enough that a Phobos-based elevator anchored to the moon and dangling toward the surface could work with existing materials like Kevlar. So, even if Earth's elevator remains distant, its siblings might rise first. But make no mistake, Earth is the prize, not just for access, but for symbolism. A space elevator on Earth would be visible from space. A thin line connecting humanity to the cosmos, a monument to cooperation, patience, and vision. And the global engineering effort to build it would dwarf the Apollo program, not in speed, but in scale and duration. It would take decades of R&D, international treaties, safety protocols, and public support. But someone has to start. And right now, in labs, garages, and university basements around the world, they already are. Not with fanfare, but with focus. Because they know this, the first step to building a ladder to the stars is believing you can hold the thread. Close your eyes. It's the year 2070. You're standing on a platform in the equatorial Pacific. The air is warm, the sea calm. Above you, so thin, it's almost invisible, a ribbon of carbon arcs into the sky, vanishing into the blue, then the black. You step into a climber, no roar, no countdown, just a soft chime and ascent. For 5 days, you rise, Earth falls away, not in a violent surge, but in a slow, serene retreat. Continents unspool beneath you like tapestries. Thunderstorms bloom and fade like living things. The curve of the planet sharpens, the sky darkens, and then silence. Not the silence of absence, but the silence of space itself. You've arrived, not by brute force, not by burning tons of fuel, but by climbing. This is the true revolution of the space elevator. It doesn't just change how we get to space, it changes how we think about space. For over 70 years, spaceflight has been an act of war against gravity brief, expensive, dangerous. Only the trained, the funded, the lucky could go, but the elevator makes space ordinary, routine, accessible, and that changes everything. Imagine orbit not as a destination, but as a place. With the elevator, we could build cities in orbit. Not cramped capsules like the ISS, but vast rotating habitats kilometers across, spinning to simulate gravity, filled with parks, schools, factories, and homes. People could live there permanently, commuting down to Earth for holidays or never returning at all. Space would no longer be a mission. It would be a neighborhood. And what would we build there? Start with energy. Gigantic solar arrays, unfurling like lotus flowers in perpetual sunlight, could beam clean, limitless power to Earth via microwaves. No more fossil fuels, no more blackouts, just sunlight converted and delivered. A single 1 square kilometer array in geostationary orbit could generate over 10 gigawatts, enough for 10 million homes. With cheap access, we could deploy hundreds. Then there's manufacturing. In microgravity, we can grow perfect crystals for quantum computers. Spin ultra-pure optical fibers that transmit data with zero loss. Assemble telescope mirrors hundreds of meters wide free from atmospheric distortion. Earth would become the home of life, and orbit the home of industry, clean, efficient, and off-planet. But the elevator's greatest gift might be what it enables beyond Earth. Today, every mission to the Moon or Mars must carry all its return fuel from Earth, a massive penalty. But with an orbital depot supplied by the elevator, spacecraft could refuel in space. Suddenly, Mars isn't a 2-year ordeal with no backup. It's a destination with a gas station along the way. Lunar bases become feasible. Asteroid mining turns profitable. Deep space probes launch weekly, not once a decade. The elevator doesn't just open Earth orbit, it unlocks the solar system. And culturally, we would change. Children would grow up knowing that going to space is as normal as flying across an ocean. Artists would create works inspired by the climber's journey. Philosophers would debate what it means to be earthbound when a thread connects you to the stars. The overview effect, the profound shift astronauts feel seeing Earth as a fragile blue dot, would no longer be reserved for a few hundred people. It would be a shared human experience. There's even a poetic symmetry to it. For millennia, humanity looked up and saw gods, fate, the unknown. Then we built rockets and conquered space through fire. But the elevator? It's gentler, humble. It doesn't conquer. It connects, like a vine reaching for the sun or a bridge woven from light and carbon. It says we don't need to blast our way out. We can grow our way up. Of course, challenges would remain. Who governs the climbers? How do we prevent orbital inequality? What happens if a habitat fails? But those are human problems. And humans solve human problems once the physics allows it. So what if it works? Then history will mark two eras: before the thread, and after. Before, we were planet-bound, peering out through telescopes and fleeting rockets. After, we became a spacefaring species, not by escaping Earth, but by building a road back home. A road that says you don't have to be an astronaut to touch the stars. You just have to take the elevator. And as you step out at geostationary orbit, floating beside the counterweight, Earth a blue jewel below, you realize something. This isn't the end of the journey, it's the first real step. Because now, the universe is open. After all this, the physics, the materials, the dangers, the dreams, comes the hardest question of all. Will it ever happen? Not could it, in theory. Not might it in some distant century. But will it, in our world, with our science, in the lifetime of people alive today? The honest answer isn't yes, it isn't no, it's maybe, with conditions. Let's be clear, no law of physics forbids a space elevator. That alone separates it from warp drives, perpetual motion machines, and anti-gravity boots. The equations balance, the forces align, the concept is sound. But physics is only the first gate. The second is engineering, and there we stumble. Because as of today, December 2025, we do not possess a material that is both strong enough and manufacturable at the scale required. Carbon nanotubes remain trapped in the gap between lab promise and industrial reality. Graphene, boron nitride, diamond nanothreads. They're all in the same boat, theoretically sufficient, practically out of reach. If breakthroughs accelerate, if we achieve defect-free, kilometer-long nanotube ribbons within 20 years, then a space elevator by mid-century becomes plausible, not guaranteed, but plausible. But if progress stalls, if material science hits a wall we can't see around, then the dream fades, not into impossibility, but into irrelevance. Because alternatives are advancing too. Nuclear thermal rockets could cut launch costs by an order of magnitude. Fully reusable launch systems like SpaceX's Starship might bring prices down to $100 per kilogram. Spaceplanes, balloon-assisted launches, orbital rings all nibble at the elevator's economic edge. None match its elegance. None promise $6 per kilogram. But they don't require a 40,000-kilometer thread of perfection either. And then there's the human factor. Even if we solve the material problem tomorrow, building the elevator would demand unprecedented global cooperation. It would require nations to agree on location, safety, access, and defense. It would need decades of stable funding, immune to political swings, economic crashes, or public apathy. The International Space Station took 15 countries and 30 years. the elevator would be 10 times harder, 10 times riskier. And the payoff, while enormous, is distant. Politicians fund what wins elections. CEOs fund what returns quarterly profits. Who funds a project whose first revenue comes in 2060? Only visionaries. And visionaries rarely hold the purse strings. Yet the idea endures, not because it's easy, but because it's right. There's a deep logic to the space elevator. It uses Earth's rotation instead of fighting it. It replaces explosive waste with quiet efficiency. It turns space from a frontier into a commons. And history shows that when an idea is this elegant, this aligned with the grain of reality, it eventually finds a way. The Wright brothers were told powered flight was impossible. Von Braun was mocked for dreaming of moon rockets. And Arthur C. Clarke, he said the elevator would be built 50 years after we stopped laughing. We stopped laughing a while ago. Now we're calculating, testing, trying. So here is the verdict, not as prophecy, but as assessment. The space elevator is not a mirage. It's grounded in real physics. But it is not yet a miracle. It waits on a material we cannot yet make. It is instead a challenge, a gauntlet thrown down by the cosmos to human ingenuity. If we rise to it, if we master the thread, then the sky is not the limit. It's the station, the first stop on a journey that never ends. But if we don't, then the elevator remains what it has been for over a century, a beautiful idea, waiting for its time. And perhaps that time is closer than we think. So the final word isn't no, it's not yet. And in science, not yet is the most hopeful phrase of all.